Okay, so it's my great pleasure to introduce our third seminar speaker in the Cognitive Science and Generative AI seminar series, Anna Ivanova, who's speaking to us today from Georgia Tech, where she is now a professor in the psychology department. Having started her career with a bachelor's in neuroscience and computer science, followed by a PhD in brain and cognitive sciences at MIT. And I'm particularly excited about this talk today because so far in the series, we've sort of skirted neuroscience. But Anna, as we'll hear, is using both tools from neuroscience and tools from AI to look at the question of the relationship between language and thought in both humans and machines. So over to you, Anna, and thanks for being here today.
Thank you so much for inviting me. And we're gonna go ahead and get started. I think there is a lot of room for discussion, and of course, I wasn't there for the previous talks in the series, but I've seen that they also, are touching upon some of the very relevant themes. So, curious to hear how the ideas there interact, and I'm assuming that this is the crowd that by now knows full well what large language models are. So, I'm gonna skip the basic introduction here and jump straight into the topic of the talk. And I'm going to start with an observation that in the last couple of years, with the rise of generative AI and specifically large language models, we are seeing this rise in what one might call AI psychology, where psychologists and cognitive scientists evaluate these artificial intelligence systems using tests that often were developed or inspired by tests designed for humans to measure reasoning, knowledge, language abilities in human beings. And in fact, a lot of such work actually now goes beyond AI and NLP. So this is just a collection of various presentations from the Cognitive Science Conference from this past year. All of them were using cognitive approaches to evaluate large language models. And you'll see that a lot of these capabilities that are being probed here don't necessarily have to do with language. So personal values, creative goal generation, analogical reasoning, these are all things that go way beyond language into broader notions of intelligence and reasoning. So now we're using large language models and these language-based assessments to really treat these models, see how well they do as general models of human cognition. So it's a pretty notable shift. But even though this specific approach is blooming right now, in some way it's not new. In some way, it goes back all the way to the Turing test, where the goal is also to use language to test cognitive capabilities, test thinking, right? So you have a human observer trying to decide whether they interact with a human or a machine through a chat interface, which is very similar to how we might interact with a large language model today. And so this idea of using language as an interface to figure out what is going on in an entity's mind is very powerful and makes a lot of sense. If I want to know what's going on in your head, the easiest way for me to do so is to just ask. But of course, even though language is a useful tool here, conflating language with the underlying thinking can be problematic. So we might end up with an issue where we might be mistaking fluent language for fluent thought. So we actually see that in pop up in a couple of different fallacies that we might see. The one fallacy is observing someone or something, be good at language, inferring that they're good at thinking. That's the fallacy we've had in human society for a while. So if you have a speaker who is very eloquent and persuasive and convincing and sounds really well, we might actually believe them even when the content of their speech is maybe a little vacuous. And then on the flip side, we might observe someone or something being bad at one aspect of thought or cognition and discarding everything else, including how good they are at language. So that's something we see a lot with large language models, especially, I guess, maybe like a year or two ago, where people would say on the internet, oh, look, it fails at the math problem, this model is useless, kind of neglecting all of the other things that these models might be able to do. And, the language abilities which they were originally arguably developed for. And so kind of the key point that I would like to drive home today is that when we evaluate large language model capabilities, we should dissociate language and cognition, intelligence, thought, however you might want to call this host of higher level non-language specific capabilities. And so I will first introduce a framework that allows us to draw that distinction a little bit more systematically. And that's the notion of formal versus functional linguistic competence with roots in human neuroscience. And then I'm going to talk about a domain that's particularly dear to my heart, which is generalized world knowledge, where you actually see those language cognition divides getting a little bit blurred, which I think is what makes it interesting. And then briefly, we're going to conclude and talk about moving forward and the implications of that framework for AI models. So we are going to start with this formal versus functional competence framework. And first of all, the question you might have is, okay, but why do we want to separate out language and cognition? Many people have an intuition that they are really tightly linked and intertwined. So why would we want to try to enforce that separation even in systems that don't naturally have it? And the answer is that we think that in humans, language processing takes place within a separate brain network. This language network responds to language at different levels of granularity, words, phrases, sentences. It responds to different forms of language comprehension, so listening, reading. It responds to different forms of language production, like speaking and writing. It also responds to sign. The location of that network varies a bit from individual to individual, but roughly this is where we tend to observe these regions. And we also know that this network responds to different kinds of languages. As long as a person understands that language, you'll see it's recruiting essentially the same network. So this is a study that looked at the language network across many different languages from different language families. And so in addition to this network responding to all different kinds of language, it's also selective for language. So if we measure how strongly these areas respond to reading, speaking, listening to language, we observe consistent, strong responses. But when we look at their responses to various non-linguistic conditions, we see actually that the responses are really low. So when it comes to solving math problems, logical reasoning, problem solving, accessing different kinds of conceptual knowledge, etc., we actually see that this network doesn't really get involved, suggesting that it is indeed specific for language. In addition to this brain imaging evidence, we also have evidence from patients who might have had damage to the language network. So these are individuals with really severe brain lesions. So here you see it taking out a huge chunk of the left hemisphere where language is typically housed. And as expected, these individuals have really severe deficits with language comprehension and language production. That's known as global aphasia. But if the damage is mostly restricted to the language regions, we actually see these individuals succeeding in all kinds of non-linguistic tasks. They might play chess on the weekend, that they can do arithmetic, they can reason about other people's minds. And so we see in patient evidence that there is a separation here. But that's not necessarily the end of the story, right? So we see this network being really core and central to language processing. But it doesn't mean that it operates independently, because of course the goal of language is to convey thoughts from one mind to the other. And so not only do you need to process linguistic information, you also need to make sense of it and integrate it with all the knowledge that you already have. And so you have a bunch of other brain regions and networks that might operate over the information that you receive through language. For example, you might use it for social reasoning and enhancing your social knowledge. You might use it to model the situation overall and keep track of characters and objects over maybe a longer narrative. You might combine linguistic information with different kinds of world knowledge that you might have learned through directly interacting with your environment. You might use language to perform general cognitive tasks like logical reasoning and problem solving. And there is a network that we are currently investigating where we might actually see its involvement in semantic tasks more generally. And so what we think happens is that there is a constant interaction between this core language network and other systems. But what's special about these systems is that they don't need language to work, whereas this one is really dedicated to language. So now that we have this kind of framework, we can ask, okay, how does each of these functions happen in the human brain? What are the computational mechanisms underlying it? Or how do they interact with one another? And then also, what about artificial models? Do they have the same capabilities? How does core language knowledge interact with all of these other capabilities in AI systems? And so in order to pose these questions more systematically, what we can do is we can divide up these capabilities into two groups. One is formal competence, which are language-specific capabilities in humans taking place within the language brain network, versus functional competence, which are non-language specific capabilities that are crucial for us to use language in real life situations and make use of linguistic information. But they can operate over non-linguistic inputs as well. If you're watching a complex silent film, for example, you might also engage your reasoning, your social knowledge, but not your linguistic knowledge. To give a little bit of more of a concrete example, we can have a sentence like the keys to the cabinet are on the table, knowing that the verb here is are, needs to be plural because it matches the word keys here, the subject. That's an example of formal linguistic competence that requires knowledge of English grammar. And so this kind of capability is actually surprisingly easy for language models, starting with maybe as early as GPT-2 and definitely GPT-3. So when you interact with a language model today, you don't really see it making grammar mistakes in English nor in other languages where it had enough training data to figure out those patterns. And that's really a remarkable breakthrough in NLP. People have been trying to build systems that can generate grammatical language for decades. It turned out that symbolic systems are really brittle and don't work for language. You need this more like a fuzzy rule pattern matching system. And so this kind of advance often goes unnoticed because people are so focused on general intelligence that they forget that this, very cool problem of grammatical language learning has essentially been solved by now. And it's not something that linguists in particular were expecting necessarily. So now large language models are an existence proof that it's possible to learn the grammar of a language without any linguistic priors being built in, without the universal grammar. So now that debate is shifting as to, how much data in reality is enough to set up that system. So, but at least in principle, we know that it's possible to learn grammar from input alone. On the functional competence side, we have this example. 6 birds were sitting on a tree, 3 flew away, but then 1 came back. There are now 4 birds. So knowing that the word here is 4 requires you to access the word form for 4, but really what you need to do is to do some basic arithmetic first in order to figure out how many birds we have now. And so that's an example of functional competence. And it turns out that these are the kinds of problems where language models are not quite as consistently good. This specific problem, of course, is easy for models like ChatGPT today. But if you increase the numbers and maybe add a couple of more reasoning steps, then you start actually seeing some performance drops. Even if these models succeed, it often turns out that success relies on memorization or basic heuristics. So they don't solve it in a way that you might expect a human to solve this kind of problem. And in fact, we're seeing that in order to make more progress in these domains, developers of AI systems are actually shifting away from pure next word prediction to fine-tuning these models on specific examples with RLHF or other approaches, or incorporating additional modules with which a large language model would interact, similar to how in the human brain you have a language network interacting with other specialized systems. And so, the success of ChatGPT, for example, was built upon the fact that it was able to be fine-tuned successfully to be helpful in dialogue, and a lot of the issues that had been observed when it first came out, like hallucination, are now attempting to be solved by pairing it with additional modules like RAG modules, where you actually don't ask the language model to do the whole thing right away. So we've seen this shift to potentially more brain-like models, which is exciting. And then if you want to hear more about this framework, we have a text paper about it with my colleague, Dr. Kyle Mahowald, my former advisor at Fedorenko, and some other wonderful people. Okay, now we are going to shift to talking about one specific domain where the formal functional competence might actually get a little bit blurry. And that's the notion of generalized world knowledge. And I've subdivided this section into a few parts. So first, we're going to talk about why it's complicated, and then we'll tackle 2 different projects that I've done in this area. One has to do with generalized event knowledge, and one is an elements of world knowledge benchmark that we've been working on in the past couple of years. Okay. So the reason why it might be hard to separate language and world knowledge is because language actually contains a lot of information about the world, lots of stuff about the world that we know we didn't observe directly, we learned about it from other people. And so that includes factual information like Paris is the capital of France, or generic statements like birds lay eggs. So if we're thinking about a model, learning them, maybe just memorizing these specific sequences of words will be enough to endow it with a lot of factual knowledge. But then another kind of knowledge is perhaps even more interesting, and that's distributional knowledge. So by observing and extracting patterns from word co-occurrences in text, it's possible to learn quite a lot about how the world operates. So for example, by observing the sentences like the sky is blue today, the sky was pitch black, the sky is pink, it's possible to construct a probabilistic representations about what colors the sky usually takes, at what time of day, which are more common, which are more rare. And so it's this kind of knowledge that we're going to be focusing on today. And an interesting thing is that distribution information that we get from language actually aligns quite well with information from other domains. So in this study, for example, they looked at co-occurrence of different object words. So in this example, animals, and also at the co-occurrence of objects or animals in images. And so when they arrange them by similarity, it turns out that the co-occurrence patterns in text and the co-occurrence patterns in images are actually remarkably aligned, which kind of makes sense if you think about it, because the language describes the world that we see. And so this kind of basic information about which animals are in the same picture or in the same sentence turns out is quite powerful for learning things about the world. Similarly, if you look at the similarity of colors in the perceptual space versus color word embeddings, there is a remarkable degree of alignment there as well, similar to kind of our sky example, maybe. But this information is imperfect because there are biases in how we describe the world around us. One such bias is known as a reporter bias, which states that we tend to overemphasize things that are interesting or important or unusual in some way. So I'm not just going to go ahead and say, hey, this morning I woke up, my alarm rang, I brushed my teeth, I put on clothes, right? I'm jumping straight ahead to stuff that's actually interesting and important and relevant here. Another example that I like is if we Google the phrase square wheels versus round wheels, we're actually getting more results for square wheels than for round, presumably because people don't need to specify that wheels are round, that's kind of implied. So this unusual case of square wheels is there, the shape is more noteworthy. So if you're imagining a model trying to learn from this kind of input, it might not actually capture the idea that wheels are typically round. And then, of course, in the brain, we know that world knowledge and just general kind of processing of word and phrase meanings is broadly distributed. So this is an example of brain responses to different words in a podcast. So a long personal narrative. And so we see that the regions that get involved are way bigger and way larger than just the language regions. And we actually see some specialization by content where pink words are words like relationship and parent and love, and green words are words like long or green or smooth, so very physical words. So we see that clearly world knowledge goes beyond just language knowledge. So we have this kind of dilemma where, okay, you learn a lot from language, but then it's not quite the same as linguistic knowledge, and that information is biased. So what do we do with it? How does it actually play out? And so the first domain is generalized event knowledge, and that is storage of templates of common events observed in the world. So a pretty prominent idea from cognitive science. And an example of that is the fox chased the rabbit is a pretty common plausible event. The rabbit chased the fox is implausible, although it's certainly possible. And then the fox chased the planet, that's something, really weird is going on there. So you have to think really hard to come up with a plausible explanation for what is happening there. By default, quite highly implausible. And the first question we asked is, does generalized event knowledge rely on language processing in humans? And so this is a neuroscience study that we did where we presented people with sentences like the fox is chasing the rabbit versus the rabbit is chasing the fox. We also showed them pictures of events like that, and they had to alternate between two different tasks. So in some blocks, they had to do the semantic task. Is this event plausible or implausible? And then in other blocks, they had to do a perceptual control task, which the stimulus was just moving on the screen really slowly. And so they had to report if it was moving left or right. And our basic hypothesis or null was that the language network is not engaged in pictorial event semantics. So we know that it responds to sentences, but would it respond to meaningful events depicted as pictures? The alternative is that it is engaged in pictorial event semantics, that it cares about meaning and not just language. And so here I'm plotting the responses in the language network to different conditions. We see that the response to sentences during the semantic condition is high, as expected. The response to both sentences and pictures during the perceptual task is low, presumably because they're focusing on the emotion so much that they don't even pay attention to the meaning. And then the critical condition I've hit for right now, right? So what is the response to pictures in the semantic task condition? Is it high or is it low? And what we found is that it's something in between. So it's lower than the response to sentences, but higher than the response to these perceptual task conditions. So we had to go with the language network is somewhat engaged in pictorial event semantics. So we didn't get a clean answer one way or the other. We then kind of wanted to see whether this is something that actually holds across experiments, and it does. So if you change the tasks a little bit, and if you change the stimuli, you get the same pattern. We also observe a similar pattern in a naturalistic event viewing or listening paradigm, where we have linguistic events evoking stronger synchronization of the language network than non-linguistic events, but still higher than control, which is just like music or kaleidoscope. But we actually see that it doesn't generalize to object categorization, where responses to object semantics are really low. So maybe there's something special about events here. And then finally, we actually have a piece of causal evidence that is critical here, which comes from individuals with global aphasia in collaboration with Rosemary Varley at UCL. We administered a version of this task to 2 individuals with global aphasia and 12 age-matched controls. And so one task we did was just match the sentence with the picture. And here, the controls performed at ceiling, and the individuals with global aphasia performed at a near chance, which makes sense because they don't understand the sentences. But then the critical task was, what about the picture plausibility judgments, right? So if you need to think about the meaning of the picture without the sentence, how do they do? And we actually saw that here, their performance was very close to the level of healthy neurotypical controls. And so we see this dissociation between the semantic task and the linguistic task in the patients. And putting all of these results together for humans, we can conclude that the language brain network is recruited, but not required for event semantics. And then we shifted to ask a similar question in large language models, right? So what is the relationship between language and event knowledge in large language models? If we take a basic set of language models trained on next word prediction, on corpus data, will they acquire event knowledge kind of naturally as a result? And so with my colleague Karina Cow, we did the study using a minimal sentence pairs approach, like giving these model sentences, like the fox chased the rabbit versus the rabbit chased the fox. The model can essentially give us an estimate of how likely that sentence is under the model. As a generative model, what is the probability of generating this particular sequence of words? And so what we assume is that the probability for the plausible sentence should be higher than the probability for the implausible sentence. And so if within each pair, the model indeed assigns a higher score to the plausible sentence, it gets an accuracy point of 1. If not, it gets an accuracy point of 0. And so then we just average these accuracies over a bunch of sentence pairs. And then what we did, we tested 2 different kinds of sentences. So one is animate and inanimate interactions. The teacher bought the laptop versus the laptop bought the teacher. And so here you see that by switching the subject and the object, the sentence becomes essentially impossible. You can kind of think of a meaning maybe, but by default, if you just read it the first time, you're like, something weird is going on here. And we see that large language models in green here do very well at distinguishing these kinds of sentences. Humans are at ceiling here in red. Large language models are not quite at ceiling, but pretty close. And we also have a bunch of baseline models, which are very basic language models before really the large language model era. And even they do quite well, suggesting that that information is very salient in the linguistic signal. We also looked at animate interactions like the fox chased the rabbit versus the rabbit chased the fox. The rabbit chased the fox is possible, but unlikely. And here we actually saw a different pattern where large language models were below human performance and below ceiling. And these baselines here in blue were essentially at the near chance, suggesting that that information is actually much harder to access in just distributional linguistic input. And so we see that there is a gap in performance between these 2 classes of sentences, which we called the gap between the impossible and the unlikely. And there are many reasons for why we might observe this gap. One is the reporter bias, right? So unlikely events being overemphasized in language input. But one thing we can do, we can actually bring it back with the formal and functional competence distinction. So one thing that's actually quite striking here is that the laptop bought the teacher, that sentence violates the selectional restrictions on the verb bought. So the verb bought requires an animate subject. Laptop is inanimate. And so when you see laptop bought, it's a very clear signal that some violation is happening here with this verb. And in this animate example, though, there isn't a clear violation that's happening throughout the sentence. It relies more on your graded knowledge of events in the world rather than a linguistic signal. And so you might hypothesize that maybe knowledge of selection restrictions falls within formal competence, and knowledge of graded events is part of functional competence. And that actually gives us testable predictions when it comes to looking at brain responses to the 2 different kinds of sentences. So stay tuned on that. And then, what I've done here is look just at very basic models, right? They're pre-trained, they're not fine-tuned. And I was looking at these probabilities. And so, what the reviewers said for this initial study is, well, what if you just ask these models, especially, the models today where you can just interact with them directly, can we, instead of evaluating the log probabilities, we ask the models, right? So prompted for a response. And then, what if we evaluate not just pre-trained models, but also instruction-tuned models, which we expect to be better at prompting, but we don't necessarily know whether they lose some of the world knowledge or not. And so that's what we did in a follow-up paper. And what we found is, first of all, the overall result is the same. We still observe the gap between the impossible events, so animate, inanimate, and unlikely events, animate. And so that kind of remains the same pretty much everywhere. Log probabilities are consistent across models. So the log probabilities results here are very similar, whereas prompting is hit or miss, right? So we looked at 3 model classes, Falcon and MPT. prompting actually failed. They were performing at chance. And then Mistral happened to be okay, and its performance was comparable with the probability of that we got through log probs, right? So even if prompting succeeds, overall, we're getting the same pattern. And so this kind of indicates that maybe the log probabilities are a good first pass to evaluate model capabilities without having to do through all of the prompt engineering to finally stumble upon the correct version that actually works. Which of course, only possible for open models where you actually have those log probabilities, because a lot of the closed models do not make the raw scores available. But overall, the conclusion from this section is, does generalized event knowledge rely on the language network in humans? The language network is recruited but not required. And then, does generalized event knowledge naturally arise in large language models? Yes, for selectional restrictions, but less so for graded event knowledge. Okay, and then we wanted to broaden beyond just events and look at many different kinds of world knowledge in this project that we call Elements of World Knowledge, or EWOC. With my colleagues Alex Satt and Ben Lipkin, we looked at a bunch of different domains that the many co-authors of that paper have put together. They are heavily inspired by what we know about human cognition, so heavily reliant on cognitive science and neuroscience studies. And another important advantage there over the study we just discussed is that now we're evaluating the probability of a sentence in context. So Ben and Alok are friends, a sentence that is likely given Ben likes Alok and not likely given Ben hates Alok. And then a sentence Ben and Alok are enemies is the reverse. So it's implausible given context one, plausible given context two. So we have this minimal pairs of pairs set up here, which is great because we know the model can just memorize a sentence to be able to generate that probability. And so we evaluated 20 open source models on all of these domains. And we saw that for the best domain, social interactions, models were doing fairly well, with the bigger, larger models approaching perfect performance, and human performance here was like essentially at 1. Our worst domain was spatial relations. So we see that here models perform at or slightly above chance, and there's a substantial gap between their performance and human performance. And, we can do the same thing for every single domain. And these are arranged from best to worst. And you see that the best domains here are social interactions and social properties, and the worst domains are physical relations and spatial relations. So knowledge of social concepts seems to be better than knowledge of physical and spatial concepts, especially when it comes to relational knowledge. And then we also briefly compared the log probabilities with prompting and essentially arrived at the same result, where for the vast majority of the models, log probability results in better performance than prompting, whether you ask to rate a sentence on a 5-point scale or choose which of the two scenarios is actually more likely. So we see it kind of maybe matching sometimes, but usually log probabilities outperform. And so the conclusion here is that basic world knowledge in large language models varies drastically by domain, with social knowledge outperforming physical and spatial knowledge. And I will say that one of the goals of the EWOC project was to provide a framework so we can actually, it's not just a set of sentences, you could actually fill in your own names instead of Ben and Alok, you can fill in different objects. And it's a way to flexibly generate new examples and maybe even introduce new concepts and new domains if you'd like. And so this really is meant to be a framework that can be expanded upon and growing going forward. Okay, so just briefly concluding, what are the implications of the formal functional competence framework for building and evaluating models of artificial intelligence. Uh, that Let me just jump that for time. There we go. So one implication is we need benchmarks that separate out formal and functional competence, because you might have a language issue that will affect your reasoning, and it's important to know where in the process an issue arises. And so, for example, the popular evaluation platform Helm, developed at Stanford, actually used to provide this kind of division, language knowledge and reasoning. I say used to because they keep updating their interface, so I'm not fully sure if it's there anymore. But I think this is like going in the direction that we're suggesting, where you have separate evaluations. They're hard to make, and often one benchmark will actually target multiple capabilities, and so then one can use stats in order to actually identify different sources of difficulty for different models. And then the second implication is that we see that the human brain is fairly modular, where you have language specialized regions interacting with other parts of the brain doing other things. So if we want a model that is human-like in that regard, we also want a model that has some degree of modularity. And I briefly talked about the fact that we already are seeing some examples of what we call architectural modularity, which is a language model paired with an external module, like a GPT plugin or some neurosymbolic approaches. But it's not the only way. You can also imagine a setup that we call emergent modularity, where you create conditions for different modules to arise within a model over the course of training by tweaking the architecture, maybe introducing multiple objective functions, maybe curating the training data, where you don't necessarily build in those modules in advance, but they kind of arise as you're training the model. And the hope there is that a brain-like model of language use would lead to human-like language use, which is useful both for engineering purposes and for us for having a good cognitive model of human cognition and language. Okay, and so overall, I think this is a really good example of a fruitful interaction that neuroscience and cognitive science can have with the field of AI, which of course has been going on for a few decades and is only flourishing more today. So just to conclude, formal competence is knowledge of linguistic rules and patterns. Functional competence are non-language specific skills required for real-life language use. This distinction is grounded in neuroscience. It helps to clarify the discourse around large language models and develop targeted assessments of their capabilities. With that, I'd like to thank everybody who's contributed to the research I've described and all of you for your attention.